Welcome to this lecture series in linear algebra. In this lecture, we'll discuss the notion of linear independence and let us recall what we need. So, of course, we will need the definitions of a field, a vector space, and most importantly, we will need the definition of a linear combination. So, if we have vectors in a vector space, let's say over a base field F, then a linear combination of these vectors is an expression of this form, where these are elements of the field F. Any such thing is called a linear combination of these vectors. And of course, so we'll assume that the reader is diligent and has done his homework, and is familiar with all the definitions. All right, so let's move on. Here are some problems for practice. And now let's get started. So fix a vector space V over a field S, and suppose we have some n vectors chosen. We say that this list is a linearly dependent list if there exist scalars such that two things. Not all of these are 0. Meaning at least one is non-zero, and this linear combination is 0. So what we are saying is that there is a non-trivial linear combination of the vectors which vanishes. The trivial linear combination would be you put 0 everywhere, then of course you will get 0, but this is asking, linear dependence is asking for the existence of a non-trivial linear combination which yields 0. That's the definition. And here we are using a list. That's just a matter of choice. Some textbooks may not phrase the definition of linear dependence quite in this fashion. All those differences are only superficial. I like to use lists when discussing linear dependence, bases, etc. We will discuss all these things later. Okay. Let's see a simple example, R2, and we have 3 vectors. And what I want to say is that these 3 vectors are linearly dependent, which means what? Again, since we have defined it in terms of list, you make this list V1, V2, V3. These 3, this list is a linearly dependent list. So we may say colloquially that, given set of vectors is linearly dependent. It just means that the corresponding list is linearly dependent. Okay, so how do we see that this is linearly dependent? So first of all, what we will do is we will express this guy as a linear combination of the remaining 2. And that is very easy. Basically, we will draw a line parallel to, we will draw a line passing through this vector parallel to this guy, and a line passing through, again, this vector parallel to this guy. And then continue. So first, let's do that. So this parallel line has been drawn, and that parallel line has been drawn, and they intersect here, and there. So we have this vector. I didn't want to use white. So we have this vector, and we have that vector. And it is clear that this plus that is that. Now, if this is V1 and that is V2, this is lambda 1 V1 for a suitable lambda, and this is lambda 2 V2 for a suitable lambda 2. Right? Because this is just a scale of that, and this is the correct scalar which gives you this point. When you scale V1 by lambda 1, you get this point. So this is lambda 1 V1, this is lambda 2 V2, and we just said that lambda 1 V1 plus lambda 2 V2 equals V, where this is V, or call it V3 maybe. So just by the parallelogram law. This plus that is that. So we have this, and now we see that lambda 1 v1 plus lambda 2 v2, and let me write a plus here and then a minus v3 equals 0, and therefore a non-trivial linear combination of v1, v2, v3 is 0, and therefore these are linearly dependent. And here is a very simple exercise. If you have 3 vectors in R2, they will be linearly dependent. Just try it out. Any 3 vectors in R2 give you a linearly dependent list. Okay. Now we move on to the notion of linear independence. Again, we have a vector space over a field F. We have n vectors chosen in V, and then the corresponding list is said to be linearly independent if, surprisingly, it is not linearly dependent. So a list is linearly independent if it is not linearly dependent. But let's decode this a little bit. Of course, it is clear, the definition is clear, but let us just spell it out a little bit more. So in other words, this list is linearly independent if whenever we have scalars such that the corresponding linear combination vanishes, we have all these scalars are 0. So the only linear combination that vanishes is the trivial one. That's what it means. Okay? And here is a very, very simple example of linear independence. Let E1 be 1, 0. This is the vector in R2, and E2 is 0, 1. Diagrammatically, this is E1 and that is E2. So then E1 and E2 are linearly independent. How do you show this? So to show this, suppose there is a linear combination that vanishes. So say alpha 1 E1 plus alpha 2 E2 is 0, which means what? Which means alpha 1, 0 plus 0, alpha 2 is 0, which by definition of addition in R2 is same as saying alpha 1, alpha 2 is 0. But 0 is just a shorthand for this tuple. 0 is just denoting the additive identity of R2, which is 0, 0. This is 0, 0, which implies alpha 1 is 0. Same is true for alpha 2. And therefore, E1 and E2 are linearly independent. And you can easily generalize to Rn or Cn or Qn or Fn, the exact same thing, which I leave to you. And with this, I want to end this lecture. It was a very short lecture, and very soon things will become very, very interesting. So as usual, like, comment, share, subscribe, and I will see you next time. All right.